Thanks for stopping by the channel today. My name's Jason. I'm KC5HWB. This is the extra class. This is the final class in the 3 classes of amateur radio licensing that exist in the United States today. Some of my most popular videos on this channel have been the technician class and the general class, which is class 1 and class 2, or level 1 and level 2, if you will. This is level 3. This is the final level. This is the top license you can get. And I want to thank the North Richland Hills Amateur Radio Club for allowing me to record this Zoom class they did at the end of 2020, beginning of 2021. It was about 8 6 to 7 hour sessions, so you're in for a wild ride today. Go through them as many times as you want to. Fast forward, stop, pause, rewind, whatever you want to do. Play them over and over again. This is good information for those of you who are currently a general and wanting to upgrade to amateur extra. Thank you to the North Richland Hills Amateur Radio Club. Their website will be linked in the description of the video below. And I hope you enjoy the video series.
Okay, here's the things we're going to be doing this morning. Modulate your transmitters. We'll go till about 10:30-ish, about an hour and a half, and then take a break, and then Wayne will do oscillate and synthesize, and then we're going to talk this afternoon about circuits and resonance, and all the fun you can have with phase angles and inductors and capacitors and resistors and other such stuff. This section we're going to now begins on page 95 in your books if you're interested in following along with it. There's some terms here that we're going to deal with. One is Modulation Index, and this first question deals with the definition of Modulation Index. And another one we're going to deal with is frequency deviation. And there are some others that we will pick up as we go along. First question is, what is the modulation index of an FM signal? And the answer is, it's the ratio of the frequency deviation to the modulating signal frequency. And B, the keyword there that will show you that it's not right, is amplitude. And C, the question is FM signals, so the type of modulation is FM, so it clearly does not have anything there. The bandwidth of the transmitted signal divided by the modulating signal frequency. You don't know the bandwidth without some calculations. So you've got frequency deviation. That's the amount of move there is in the carrier with the modulation. And the modulating signal frequency is, if you're sending a pure tone, is whatever that frequency is of that tone. So that's how we begin this process. Okay, the second question: how does the modulation index of a phase modulated emission vary with carrier frequency? And all of the answers have carrier frequency. That's a third frequency that we're dealing with. That's the frequency that you're transmitting on. And the modulation index does not depend on the RF carrier frequency. Answer is D. What is the modulation index of an FM phone signal having a maximum frequency deviation of 3,000 hertz either side of the carrier when the modulation frequency is 1,000 hertz? And if you go back to the question before, it's the 3,000 divided by 1,000, which is 3. I don't know how to get that thing to allow me to work with it. We'll just have to move on and not play with the computer for a while. Okay, what is the modulation index of an FM phone signal having a maximum carrier deviation of plus or minus 6 kilohertz when modulated with a 2 kilohertz modulating frequency? And again, it's 6 divided by 2, which is 3. And it's that simple math coming out of that first definition. What is the highest modulation index permitted at the highest modulation frequency for angle modulation below 29 megahertz? I had to look up angle modulation. Anybody know what it is? Angle modulation is either phase modulation or frequency modulation. They have very similar characteristics. And the answer to that is a modulation index of 1. That limits the bandwidth of an FM signal below 29 megahertz. And it's going to look an awful lot like phase modulation, even if it is frequency modulation with that low modulation index. Have about the bandwidth of an AM signal. There is a little trick in this question, and that is at the highest modulation frequency. So if you're doing typical voice that has components up at 3 kilohertz, then your deviation can't be more than 3 kilohertz. Deviation ratio. This is another definition. It's different from the modulating index. And this one is the ratio of the maximum frequency deviation to the highest modulating frequency. So that's the deviation ratio. If you've got a voice signal that's modulating the carrier, then you're going to figure 3 kilohertz for voice as the maximum or the highest modulating frequency. And then the maximum carrier deviation is the other piece in that ratio. And the carrier frequency has nothing to do with it here either. So and it has nothing to do with just the frequency components of the audio. It's the ratio between the deviation and the audio modulation. What is the deviation ratio of an FM phone signal having a maximum frequency swing of plus or minus 5 kilohertz when the maximum modulation frequency is 3 kilohertz? And it's going to be the 1.67, which is the 5 divided by the 3. Which is, what is the deviation ratio of an FM phone signal having a maximum frequency swing of 7.5 kilohertz when the maximum modulation frequency is 3.5 kilohertz. And this takes a little bit more math. But if you divide it out, it becomes a 2.14. And you can actually approximate that in your head if you take the round the 7 down, or the 7.5 down to 7 and divide it by 3, you'll get 2. So you know it's a little more than 2. And it's definitely not 47.
Yeah, it's just divide the 2 by each other, 7.5 by 3.5.
I'm sorry, I didn't catch that, Craig.
It's just the 7.5 divided by 3.5.
That's
like
correct.
Yeah. So, and then just round the numbers, you choose 2. So,
yeah, my engineering mind rounds things up and does approximations, which gives me the answer without doing the calculation.
Yeah. As I said, 7 divided by 3.5 is 2. So you're in ballpark there.
Yeah.
Can you guys let us know when you move on to the next question? Because I'm like one question behind you guys when you guys just move on to the next question, because I'm still on B05 and you guys are on B06, and I'm still trying to figure out what you guys are talking about, and you guys move on and I don't know what the hell question you guys are on. So excuse my French, but I'm trying to keep up and you guys are like one question ahead of me. So I'm trying to figure out the math and all that stuff. And
okay, we can do that. Are you not seeing the
I'm trying to follow in the book and highlight the book and stuff, and I'm
okay.
I'm not able to keep up with you guys. So
I understand that looking in the book and not watching the screen. Anyway, we're going to move on to the next question.
Okay, can we start off with can we go back to the B06, please?
Okay. Do you have a question?
Yeah, can we go over the math on this one so I can
okay,
up to speed on this, please?
In your calculator, you put in the 7.5 and you divide it by the 3.5 and it comes out to 2.14, which means A is the answer.
Okay, great. Thank you very much. I appreciate it.
Okay, you're welcome. I appreciate the interruption, and we want to be helpful, not confusing.
Thank you. I appreciate that. And sorry for my French.
The next 8B10, the E is for extra pool, and then the B8 is the 8B is the segment, and the 10 is the question number in it. What is frequency division multiplexing? And the answer is B, 2 or more information streams that are merged into a baseband, which then modulates the transmitter. And Kevin, what page is that on?
Page 99. The top of page 99.
Yeah, I've got it. I want to call people's attention to it. This is one of those crazy things that, Wayne, can you explain all of the stuff that they're talking about here? 2 or more information streams merged into a baseband, which modulates the transmitter. What are information streams? I guess that's 2 audio signals.
Okay, well, that would be where you've got, it's very similar to cable TV transmission, which uses FDM. What that is, you've got many little carriers at different carrier frequencies that are all put together in the 2 megahertz bandwidth for cable TV. And each of the little carriers is an information stream. It's all digital modulation merged into a baseband. And it's all done in DSP. This is pointing toward DSP type applications. Frequency division multiplexing is where you put different information streams. Another application is the telemetry that comes from spacecraft, satellites, Apollo, manned spaceflight missions in Apollo or Gemini. The telemetry that the ground gets back are from many different sensors. And some of those are frequency division multiplexed, where each sensor takes on a different carrier frequency. Another application is multi-carrier telephone lines, which were the first attempt at getting more than one analog signal on a twisted pair, like to reach out into the country and, into the spaces away from big cities, which we called the country back then. So that was years and years ago when that system was in use. And every like 10 kilohertz up to about a couple of hundred kilohertz, there would be an analog signal, which is a voice channel. And at the user end, that would be translated down from the 100 kilohertz range back to baseband, which is the 3 kilohertz phone bandwidth. That's a good example of frequency division multiplexing.
Okay, so the SCA carriers on a FM broadcast station would be another example of that frequency division multiplexing.
Yes, exactly.
What they do there, gentlemen, is they transmit agricultural information or pipeline information or whatever on the same carrier as a broadcast FM by using a subcarrier that is, I believe, somewhere around 90 kilohertz, which is above anything that the audio is going to, FM audio is going to deal with. And FM stereo does a similar thing by using subcarriers to transmit the left and right channels. Okay, that makes sense. So the information streams could be music, it could be digital, it could be telemetry, it could be left and right channel stereo, and they put that all into a signal that if you looked at it would have all these subcarriers, and you demodulate each of the subcarriers to retrieve it, and then that's called a baseband, and then it modulates the transmitter, which gives you a very complex signal out there. And that's frequency division multiplexing. And is there any answer in that that's likely to confuse? It's not in packets. It's not frequency hopping, and it's not nearly as complicated as pulse position modulation, which we don't want to go into here. So the answer is B. Okay, we're going to 8B11. What is digital time division multiplexing? And what happened to the D answer to that question?
Got cut off, but I don't think you'll need that one. This is time division multiplexing is where you have assigned slots to each of your information streams, assigned slots in time. That is, if there's a good example in the book, page 99, if you look at that, where you've got a synchronizing signal, which would be a sync pulse, and then it shows 6 different time slots within the information that it's transmitting, and each time slot is assigned to a different information stream. Some can be analog, some can be digital. It's just that each information stream gets its own time slot.
Okay. I wonder how when I copied that, I got that messed up. Anyway, answer is B. It's 2 or more signal arranged to share discrete time slots of data transmission.
Hey, John, I need to take a break for a couple of minutes. I'll be right back.
Okay, appreciate your help with these two. Which of the following is a type of analog to digital conversion? And analog would take an audio signal and the output would be a series of numbers, like a wave file on a computer, that would give you the information in that analog signal in a way that it could be converted back after it got transmitted. And the answer is A, it's successive approximation, which you have a sampling rate every so much of a fraction of a second. You measure the voltage in that analog signal in effect, and then convert that to a number, a digital number, binary number. And it's successive approximation because in that little time slot, there may be a shift in the amplitude of the signal. And what you're really doing is measuring the, depending on the system, the average or the peak of the voltage in that. I don't know what a harmonic regeneration is, level shifting, I don't know, phase reversal. It really is just the successive approximation that makes sense in this question. Okay, A11. Which of the following is a measure of the quality of an analog to digital converter? And the answer is total harmonic distortion. The lower the harmonic distortion, the higher the quality of the digital. Peak envelope power has nothing to do with analog to digital. Reciprocal mixing, I don't know what that is. Power factor is a thing we'll talk about this afternoon, but it has nothing to do with analog to digital. Okay, 8A01. What is the name of the process that shows that a square wave is made up of a sine wave plus all its harmonics? And the answer is A, which is Fourier Analysis. In broad general terms, Fourier Analysis is taking a signal and breaking it into its spectrum so that you shift from a time domain, voltage versus time, to a frequency domain, which is amplitude versus frequency. That's the class in engineering that I did not take. And it's the only class in engineering that I regret not taking. But Fourier Analysis is the answer to that question. I wonder what's happening with is there a white blank on your screen? Do you see that whole question?
Yeah, let me see. I see the whole question.
I see what's happening. That is my 9:30 Skype meeting coming in on me. The next question also deals with the Fourier analysis, and it's what type of wave does a Fourier analysis show to be made up of sine waves of a given fundamental frequency plus all its harmonics? And the answer is a sawtooth wave. And for most of us, the best way to deal with this is just remember a sine wave and all its harmonics is a sawtooth. West has a thing about a symmetrical sawtooth in his notation on this question, if I remember correctly. Okay, 8A05. Which of the following instruments would be the most accurate for measuring RMS voltage of a complex waveform? RMS stands for root mean square, which is a term that really talks about the effective voltage of an AC signal or even a complex waveform. And a grid dip meter measures resonance in a coil. The D'Arsonval meter is your old-fashioned coil and a magnet meters that everybody used to have. I don't know what an absorption wave meter does, but the answer to this is D, a true RMS calculating meter. And that would be a meter that would analyze the signal and then calculate the root mean square voltage over time. For AC power, the root mean square, if you talk about 120 volts sine wave, the root mean square voltage is what that 120 volts is. The peak voltage in that's about 140 volts. A807, what determines the PEP to average power ratio of a single sideband phone signal? And the answer is B, the speech characteristics. The PEP is the peak envelope power. That's the maximum, the peak power in the modulation envelope. And that has nothing to do with the frequency of the signal. It has nothing to do with the carrier suppression, because the assumption with single sideband is that the carrier is 100% suppressed. The power ratio has nothing to do with amplifier gain. It's the speech characteristics. So if you've got a well-modulated heavy voice, it's got a higher average, and the PEP to average ratio goes down. What is the approximate ratio of PEP to average power of a typical single sideband signal? And they say it's 2.5 to 1, and I'm not sure who did that analysis. But this is one that I think most of us would have to just memorize that particular particular answer. And we're talking about a well-modulated single sideband signal, not a one where you're whispering into the microphone. It would almost always be higher than 1, because the peak envelope power would be those points where your sound volume in a particular syllable is the greatest. And the average power has got to be less than that. Which of the following can be used to generate FM phone emissions? Well, balanced modulators are used to eliminate carriers. So you don't do that in FM. So A and D are automatically out of it. Reactance modulator on the final amplifier is not going to change frequency at all, so it does not modulate. So the answer is B. It's a reactance modulator on the oscillator in the transmitter. A reactance modulator uses a change in either inductance or capacitance with voltage to change the frequency of the oscillator, and that provides the modulation. Typically a little varactor or what's the other term? Varicap. Across the tune circuit in the oscillator is the way that's accomplished. What is the function of reactance of a reactance modulator? And the answer is D, to produce phase modulation or frequency modulation signals, angle modulated signals, by using an electrically variable inductor or capacitance. That's what I talked about before in that previous thing. Reactance modulation, the reactance, the change in reactance changes the frequency of the tune circuit in the oscillator. It uses either, well, typically it's going to use capacitance, but it could use inductance to do it. But it does not have anything to do with resistance. It's not doing anything with AM. It's not amplitude modulating. So the answer is D. Okay, 70 E05. What circuit is added to an FM transmitter to boost the higher audio frequencies? And it's an equalization circuit that is a pre-emphasis network. And the way to remember that is it emphasizes the higher audio frequencies. De-emphasis would be to reduce instead of boost. And I don't know why they put heterodyne in the answers to confuse. But boost audio is emphasis, pre-emphasis. 70E04. What is one way a single sideband phone signal can be generated? In the old days, there were two basic methods. One was called phasing, and the other was called was filtering basically. And you're talking about a single sideband signal, which is an AM signal, suppressed carrier, and only one of the sidebands. And the balanced modulator gets rid of the carrier, and the filter chooses one sideband over the other. Very, very sharp filter. You don't want to use a reactance modulator on sideband. I don't know what a loop modulator is. And a product detector is going to give you audio output even with a double sideband signal, but it does not give you single sideband. So the answer is A.
So basically the only right answer has the word filter in it.
Yes.
Cool. That's how I'm going to remember it.
Excellent. Yeah, thanks for sharing that little observation. What is a common method for generating an SSB signal using digital signal processing? And the answer is D. Signals are combined in quadrature phase relationship. Does that phrase make any sense to everybody?
Not in the least.
West talks about this being a modern way of doing the phase modulation to generate single sideband. What they did in those days is they split the audio into two components, one 90 degrees out of phase with the other. And they split the carrier frequency into two signals and phase them 90 degrees apart. And then they combine those in a double balanced mixer. And the output came out as either upper sideband or lower sideband, depending on how they fed those into the mixer. And what is happening with the quadrature is at 90 degrees. Quadrature phase is 90 degrees. And I saw a really inexpensive, I think it ran about $60, single sideband transmitter kit online that used Class E amplifier, which we'll talk about in amplifiers, and a high a divided down set of digital signals so that they could produce the 90 degree separation, the quadrature phase relationship in the carrier in order to be able to receive single sideband. It was an interesting combination of a direct conversion receiver and the quadrature phase thing that allowed the receiver just to receive one sideband or the other. So in dealing with this, the mixing products are, mixing products are converted to voltages and subtracted by adder circuits. What you're doing is, a digital signal. So we're not talking about converting things to voltages. Frequency synthesizer does not remove sidebands. And I have no idea what varying quartz crystal characteristics emulated in a digital form mean. So the answer is D, gentlemen, if that helps. Okay, 7F03. What type of digital signal processing filter is used to generate an SSB signal? And the answer is a Hilbert transform filter. Kevin, what page is this question on?
It's on 103.
Yeah, okay, that's where I actually landed. F03. When I was working in the engineering department at RCA in Florida years ago, we had a salesman who came in and tried to impress us by using some of the technical names for filters. And my look at this Hilbert transform filter reminds me of that experience. When the salesman was gone, the engineers all agreed that he was trying to impress them by using that kind of a really non-standard name. And the question, the book says the Hilbert transform filter is a digital signal processing filter that performs an operation on an analytic signal, which is a signal containing both the I and Q components. It is a high-tech version of the old phasing method of single sideband generation, which was popular before the crystal filters were readily available. And West notes that all the old becomes new again in amateur radio. This is one you just have to remember. And I guess the word transform is that. A notch filter just notches out a very narrow band of frequencies. It's used in receiving to get rid of carriers that are interfering, and an elliptical filter is a type of filter, but it's this C Hilbert transform filter that is the answer. Okay, 7E07. What is meant by the term baseband in radio communications? And from our discussion earlier, the answer is B. The baseband is a frequency range so that if you're modulating an FM signal with a 100 kilohertz subcarrier. It's that frequency range that's being used prior to modulating the FM transmitter.
I don't see the difference between that one and the next answer, between B and C. An unmodulated bandwidth of the transmitted signal.
Okay. What's the bandwidth of a carrier? The bandwidth of a carrier is going to be very, very narrow because it's unmodulated. It's just a single tone out there on a single frequency. If you do the most simple piece of this, I didn't catch who's asking this question, but if you do the very simple thing of, okay, we've got the simple baseband would be one signal, okay? That signal is your voice, for example. And B is the frequency range that's occupied by that audio signal before it's modulated. So that baseband would be from about 200 hertz to 3 kilohertz. That's the baseband frequency for just a simple voice transmission. The unmodulated bandwidth of the transmitted signal, no modulation, just a carrier. And the bandwidth of that is going to be very, very narrow. It's going to be, in theory, just a fraction of a hertz. So does that help? They're talking about two different things. They're talking about the frequency of the audio signal. If you
We'll
use,
have to spend a little more time on the definitions of the baseband and bandwidth.
well, baseband would be, for example, just in terms of simple audio, if you know, not talking about additional subcarrier frequencies, just the baseband of a simple audio signal. If you're talking along and your speech is going to be in the 200 to 3,000 hertz range, okay? That would be the baseband. But if you had a piccolo player who came in and began playing notes on the piccolo behind you into your microphone, that signal baseband would increase to the frequencies of the piccolo, which are going to be up in the order of 5 to 6 to 10 kilohertz. So your baseband would then be from 200 up to the 6,000 or 7,000, as opposed to the, you see what I'm saying?
I was thinking that the voice and or the piccolo is what's doing the modulation.
Yeah, but that audio signal prior to modulation is the baseband. The frequency range of that is the baseband.
Well, and the next one, it says the unmodulated bandwidth, and it seems to me those are the same thing.
No, if you've got an unmodulated signal, what is it?
That's the frequency you're broadcasting on.
Transmitting on. We don't broadcast in ham radio. Yeah, it's the frequency you're transmitting on. It's no modulation on it. What's the bandwidth?
Your frequency.
Yeah. Does it have sidebands?
No.
Okay. It'll have sidebands on when it's modulated.
Okay, but the other one, it says the frequency range occupied by the message prior to modulation. Wouldn't
Right.
that just be the base frequency?
Yeah, but it's the audio signal.
Yeah. All right.
It's not the transmitted signal, it's the audio signal.
Okay. So I'm looking at I'm comparing the audio signal with the transmitted signal, and that's where I'm confused. All right, I got it now.
Okay. That's an important thing for us to be able to do, is to help you distinguish what that is, because if you know the definitions, the answers are obvious. If you don't know the definitions, then you're having to guess. Okay, how are we doing time wise? We're about on target, because I've got 30 minutes and we're 30 minutes in. Okay. E1B01. Which of the following constitutes a spurious emission? The answer is D, an emission outside the signal's necessary bandwidth that can be reduced or eliminated without affecting the information transmitted. Typically, it's going to be things like intermodulation products or splatter due to nonlinearity in an amplifier, or harmonics of the transmitting frequency. Those kinds of things are spurious emissions. If you look at the others, an unidentified station transmission may be illegal, but it's not spurious. A signal transmitted to prevent its detection by another station other than the intended recipient is illegal, but not spurious. Any transmitted signal that unintentionally interferes with another licensed station, that's called QRM. It's the D, outside the signal's necessary bandwidth, that is the answer to this one. Okay, 1B08. What limitations may the FCC place on an amateur station if its signal causes interference to domestic broadcast reception? And there's a caveat in here, assuming that the receivers that are being interfered with are of good engineering design. The answer is D, the amateur station. FCC may declare what's been called quiet hours when the station cannot transmit on frequencies that cause the interference. And this is usually applied when the amateur just really doesn't want to cooperate. And the quiet hours are really determined by the engineer in charge at the FCC. It's not going to be can't transmit or operate at all, and it's has nothing to do with the 30 megahertz. It's just having the quiet hours, the certain hours that cause the interference. all I want to say on that. What type of amplifier circuit is shown in figure E7-1? Let's talk a little bit about transistor circuits. This is an NPN transistor. The arrow is the emitter. The other side of the line is the base, and the top piece up there is called the collector. What happens in this circuit is that signal coming in, the DC on that signal is blocked by the C1 capacitor, but it has a low enough reactance that it will pass the audio component or RF component into the amplifier, and the signal, the emitter, will track that signal because it's positively biased diode for an NPN. And the voltage on the output at the emitter is, for an NPN, typically 0.6 volts below the base. And common here means referred to the signal ground, which is shown by this little ground symbol. It's the return for the DC. It's the ground for the signal. So you pull the signal off the ground into the output. Common would be as referenced to the ground. So this circuit is not an emitter follower. An emitter follower would have no resistance in the collector circuit. So you can eliminate the emitter follower. So it's a common amplifier of some kind, obviously. So which of these is the signal basically grounded? Is it the base, the collector, or the emitter? And the answer is that it is the emitter, but it's got a resistor in it, you say. Well, the component, the capacitor, has a very low reactance to the signal frequency, which basically grounds the emitter, even though the DC bias is set by the resistor. So this is C, a common emitter amplifier, even though that resistor there kind of confuses things a bit. Does that make sense?
Clear as mud.
Okay.
Easy way to remember which leg goes to ground. Your emitter leg goes to ground.
Beautifully summarized. All of that stuff I said could have been said just in that. The emitter goes to ground, and it goes to ground through, signal goes to ground through the capacitor. Okay, 7B10. In figure 7.1, again, what is the purpose of resistor R1 and R2? The answer is B. It's a voltage divider that takes the power supply voltage up here at the plus, and the ground, and does a voltage divider thing, and the ratio of these will be the voltage on the gate of the, or the base. Gate is the thing that applies to field effect transistors, but it's the base of the transistor. And typically this is adjusted in conjunction with the gain of the transistor and the ratio of the two resistors, so that the voltage on the collector is halfway between the power supply voltage and ground, which gives you the maximum range of operation for the amplifier. That's how it's designed. But this is a voltage divider bias for the transistor. We'll look at self-bias in a later question. It's not feedback, because if feedback would, R1 would come from the collector back, it actually comes from the power supply, so it's a voltage divider. And they're not load resistors. Load resistors have to do with the output. A load resistor would be out here off the output and down to ground. So it's voltage divider bias. Still staying with question E71, what is the purpose of R3? And the answer is D, it's self-bias. If you removed R2, the divider would not be as stable, because the gain of the transistor would determine where the emitter voltage point was, and it would be dependent on the thing. But the R3 is self-bias. It's not a load resistor. The emitter bypass is the capacitor, and it's not a fixed bias, it's self-biasing. I guess that's all I want to say on that. 7CO1. How are capacitors and inductors of a low-pass filter pi network arranged between the network's input and output? And I want to refer you to page 105 here, and the diagrams that are there. A pi network is one where you have 3 elements, and it looks like the letter pi if you eliminate the ground line at the bottom. So it's called, that's why it's called a pi network. It looks like the Greek letter pi. And you see in that diagram 2 capacitors, one on the input, one on the output, with an inductor in between. And that is a pi network low-pass filter. And the answer is D. A capacitor is connected between the input and ground. Another capacitor is connected between the output and ground, and there's an inductor in between it. And I remember this basically as a, from the standpoint of the old brute force, high voltage power supplies in tube type rigs, because you put the output of the voltage rectifier across, put a capacitor across the output of it, you put a big heavy multi-Henry choke on it, and you put a capacitor on the output, and it filtered out the AC component and left just the pure DC, supposedly, on the output. One way to remember this is that the capacitors basically short out higher frequencies, and they do less shorting out of lower frequencies. And the inductor passes lower frequencies, but does not pass higher frequencies. It has a higher impedance at higher frequencies. So what goes through is the low frequencies, thus low pass filter. So the answer here is D, a capacitor is connected. I read that, we'll move on. Which of the following is a property of a T-network with series capacitors and a parallel shunt inductor? And that's the thing in the diagram where it says T-network high pass on the left side on page 105 on the top row, 2 capacitors in series and an inductor between. And this is a high pass filter, which is C. The high frequencies are conducted through the capacitors. The low frequencies are shut down. The inductor will short out lower frequencies and allow the higher frequencies to pass because it has a higher impedance. What advantage does a series L pi L network have over a series L pi network for impedance matching between the final amplifier and a vacuum tube transmitter and antenna? Is there a diagram for that? No, there's not a diagram. Basically, the more elements you have in a filter, the better the filtering is done. But the purpose of the filter is going to be, especially in a tube type vacuum thing, is harmonic suppression. And it will have an L pi L network, would be a pi network with an inductor in front of it and an inductor after it. It's not going to have higher efficiency in terms of what it passes through because of the resistance in the coils in the inductors. It does require a capacitor. In fact, it requires 2 capacitors. The transformation range has nothing to do with it, so it really is the greater harmonic suppression. Okay, which describes a pi network used for matching a vacuum tube final amplifier to a 50 ohm unbalanced output. And basically what it is here is just describing the network, a pi L network with an additional, it's a pi network with an additional series inductor to the output. And what there really is, what is the description of that? And it's that. And I don't know what the phase inverter load network is. That's a bunch of gobbledygook. It's got 4 components. The pi network has 2 capacitors and an inductor, and then the series inductor after that. So the C is clearly not the answer. And the pi network is not going to have all components isolated from ground because the capacitors are grounded on one side. So B is the answer. What is one advantage of a pi matching network over an L matching network consisting of a single inductor and a single capacitor? And the answer is A, the Q of the pi networks can be controlled. The Q of an L network depends on the antenna, and the pi network allows the Q of the circuit to be controlled by the tuning capacitor. L networks can perform impedance transformation. Pi networks are not more stable. You've got passive elements in them. Pi networks do a better job of filtering. Pi networks provide balanced input and output. We're not talking about balanced here at all, and pi networks are not balanced. The capacitors are grounded, so it's unbalanced. And the answer still is A. Which of the following describes how the loading and tuning capacitors are to be adjusted when tuning a vacuum tube RF power amplifier that employs a pi network output circuit? Has anybody here, how many people here have used a vacuum tube amplifier?
Me.
Yeah, well, power amplifiers are, as add-ons are one thing. The power amplifiers that were built into our transmitters back in the 50s and 60s, the tuning process. The tuning process was that you keyed the transmitter into a load. You tuned the tuning capacitor for a dip, minimum capacitance. You typically started with the output capacitor at its or the loading capacitor at its maximum. And so the tuning capacitor would, you tune for a dip, and then you would adjust the loading capacitor and then retune the tuning capacitor until you finally got the plate current up to whatever the power level that you were trying to use. Permissible plate current might be the allowable plate current, but it also might be the plate current that kept your transmitter from exceeding the power permitted for novices. Some novice transmitters would run 90 watts input power, and you were only allowed 75 watts in those days. So the answer is D. The tuning capacitor was set to minimum plate current, not capacitance, so B is wrong. The loading capacitor is adjusted to minimum plate current while alternately adjusting the tuning capacitor for a maximum allowable plate current. It's the reverse of that, basically. So the one that seems to be the same as D, the loading capacitor is set to maximum capacitance and the tuning capacitor is adjusted for minimum allowable plate current. That's the starting process, part of the process, but D is the answer. It's the loading capacitor needs to be adjusted so it's not just set to maximum capacitance. That's the thing that makes that one false. Now, have I made that so complicated nobody understands it, or does it make sense? We're going on. 7C04. How does an impedance matching circuit transform a complex impedance to a resistive impedance? And the answer is C. It cancels the reactive part of the impedance and changes the resistive part to a desired value. Negative resistance does exist in the world, but it's not used in an impedance matching circuit. A negative resistance circuit is going to oscillate. It does not introduce transconductance to cancel the reactive part of the impedance. And it's not dissipating reactive currents. It's canceling the reactive and changing the resistive part, C. What causes intermodulation in an electronic circuit? The answer is nonlinear circuits or devices. Intermodulation can be measured in stereo audio equipment and you want it to be as low as possible. So you want that linear amplifier. So they'll use a 500 watt amplifier so that the linear portion of its operating curve is where it operates most of the time, even though the output that they're shooting out of that 100 watt or 500 watt amplifier is 20 watts into the speakers. And positive feedback causes oscillation, lack of neutralization, has to do with spurious signals. It's the nonlinear circuits. And it's the linearity of an amplifier circuit like a vacuum tube or a transistor. The most nonlinear circuit is a diode. What is the term for spurious signals generated by combining two or more signals in a nonlinear device or circuit? And the answer is intermodulation. It's two signals that get combined in a way that you don't really want them combined. For D03, how can intermodulation interference between two repeaters occur? The answer is B, when the repeaters are in close proximity, like on the same tower, and the signals mix in the final amplifier of either of the transmitters. You get intermodulation, and depending on the frequencies of the transmitters, where that intermodulation comes out is dependent on those signals. And doesn't deal with signals causing feedback. It's the signals mixing. C is a fun answer. The signals from transmitters are reflected out of phase from airplanes passing overhead. I suppose that's a possible scenario, but the signals coming back are going to be pretty weak. And the same thing is true with the airplanes passing overhead in C and D. Forget the airplanes. It's the mixing and the amplifiers. Which of the following filters would be a good choice to use in a 2-meter band repeater duplexer? It's not a crystal filter. It's not a digital signal processing filter. It's not an LC filter, technically. It's a cavity filter. Cavity filter is a cavity that is resonant at one of the frequencies in the repeater. And basically, cavity filters are put together so that the transmitter frequency is attenuated at the input of the receiver on the repeater, and is the my mind has turned to mush. Basically, the cavity filter, because of its physical resonant cavity thing, is a very, very sharp filter. So 600 kilohertz with cavity filter can give you enough gain that the output of the transmitter doesn't interfere with the receiver. Which of the following may reduce or eliminate intermodulation interference in a repeater caused by another transmitter operating in close proximity? The answer is B, a properly terminated circulator at the output of the repeater's transmitter. Class C amplifier and Class D amplifier are amplifiers where the output signal is not a sine wave, and intermodulation from those could be horrendous. And a bandpass filter in the feed line between the transmitter and the receiver. I don't really know what that means. The answer, is the circulator at the output of the repeater's transmitter, which keeps the reflected and common mode currents and stuff at a minimum. What current, this is E4E08. What current flows equally on all conductors of an unshielded multi-conductor cable? And N0FYE and I have had some extensive conversations about common mode current. Which is the answer to this question. I don't know what differential mode current is. Reactive current only is not the answer. Return current is not the answer. Common mode current is, well, for example, the best example in ham radio is the coax that feeds a half-wave dipole, and without a modem, or not modem, a balun. What happens is you've got a third conductor up there that's not, you don't think about it, and that's the outside of the coax, and the common mode current comes back down the coax and gives you some hot RF in your shack. And you can actually feel that if you're running 100 watts on HF.
Quick question, John Park.
Yes.
Your page number.
I don't know. What is the page number?
It's 109.
109.
Thank you. I had to step out and I got lost. Sorry.
Fair enough. And whoa. I was not expecting that to be the last question in this, is it? It is.
It is the last question.
It is the last question. It's time for a break.
The one I want is this one. So everybody can see it. You've got it on a tablet. You've got it someplace you can refer to it. And then we'll be going down through the questions in the book at the same time. And then review the questions at the end. We'll end at noon. This is not a long section. And we can get done and then go to lunch at noon. That's where we're headed. Let's see, I need to get rid of that. No, I don't want to compress. I don't like all these new versions of Adobe Acrobat Reader. Okay, so we're going to oscillate and synthesize, and then they throw in, Gordon West throws in a section on DSP operations and everything you can do with it. So you can see my screen. The top left, we start with the public address system, the sound coming out of the speaker. Can everybody see this on your screen?
Yes, sir.
Okay, thank you. And also I want you to be able to take notes. That's why we suggested to print it. If you can't do that, then take notes in your book. I'll tell you kind of which question we're on so you can take notes on it, because that'll be very useful in your review for testing. But when the sound comes out of the speaker, that's the top left of the page I'm looking at. Everybody knows that this little triangle with a line in and a line out is an amplifier. Sound comes out of the speaker, bounces off the wall, gets back to the microphone by whatever mechanism. It bounces off of it. The microphone's pointed toward a wall that the sound is bouncing from back to the speaker. The mechanism of producing the howling noise is feedback. The noise you hear is oscillation. So we need to get those two concepts separated. The output, the speaker is howling, that's the oscillation. The mechanism of getting to that sound bounced off something and then back into the microphone is feedback. And the microphone picks it up and amplifies it even more, and it just becomes a howl. A high frequency pitch, very annoying when the speaker is trying to speak. The next little circuit down is one that we introduced last week in the receivers, where we made a local oscillator out of an oscillator. You have an amplifier, which is again the triangle. You have, this is an LC oscillator, and the bypass capacitor is sitting here so you don't short out, make a DC short through the choke from the output of the amplifier back to the input. If you did that, the amplifier is probably not going to work, may damage or destroy the amplifier. And so you have to have a bypass capacitor. Now let's define what a bypass capacitor is. A bypass capacitor is a very low impedance at the frequencies of interest. At the signal frequency running through this circuit, the bypass cap is a low impedance. In RF circuits, it doesn't take much capacitance, a 0.01 or a 0.001 microfarad capacitor to make a short circuit. At VHF and UHF, 100 picofarads is a short circuit. At audio, it takes, depending on the impedance of the circuit, 20 to 100 microfarads to get a low impedance. And here, the bypass capacitor blocks the DC from one side of it to the other, because capacitors don't pass DC, they block DC. but it does let the signal frequency through. Any questions? So in this little oscillator we used here last week, I didn't show the details, so here's the details. You have an input to the amplifier, you have an output of the amplifier, and the output signal goes through this tuned circuit back to the input. That action is feedback. So if you're designing an oscillator, analyzing an oscillator circuit, it's very important to identify the feedback path. And that's what we're going to be doing. We're going to be looking at these oscillator circuits, and I've copied them down here from page 41 of the Gordon West book, Studying the Amateur Extra Class License Preparation. And I did note down there at the bottom, if this thing will quit popping up, that page 141 is where I got it. That's also the beginning page of this section on oscillators and synthesizers. Now, one thing we're going to be using is a crystal oscillator. I've drawn a picture right here. That's my own picture, so it's not copyrighted or attributable to anybody but my poor drawing skills. What it is, it's a disc, kind of like a coin. A coin, a 10-cent dime, is a disc. And this disc is made out of quartz. It's called a quartz crystal. And how this works is there's a patch of metallization on each side so that you can put voltage across this disc. And there's a lead attached, a wire lead attached to it, so you can get it connected in your circuit. The way the quartz works is you put voltage across it and it changes the size of that disc. The disc is has a thickness, and so you put voltage across it and there's a piezoelectric effect that actually changes the size according to the voltage across the disc. Now, there's a question about piezoelectric effect, and that's what we're going to be talking about. The disc has a mass, and the mass is like any other mass in physics. It has inertia. The inertia of a quartz disc is called motional inductance. Inductance in electric circuits is just like inertia in physics of masses. And there's also a part of the operation of the quartz disc that is motional capacitance. That is, the solid quartz blank that makes the crystal can soak up high frequencies like a capacitor. And so if you look there, top left side down a little bit, this is the electrical equivalent circuit of a quartz crystal. It has motional inductance, it has motional capacitance, and that inductance and capacitance primarily sets the resonant frequency. It also has a resistance in series, which is a loss. Any resistance that you run electric current through produces a loss. There's also a capacitor in parallel. It's called a shunt capacitor, and that is the packaging capacitance that's in parallel and connected to the two leads coming out of the crystal. See, the two lines coming off the crystal model are the two leads as represented in my attempt at this drawing of the quartz disc. There's some good pictures of it on the internet. If you go Google like quartz crystal, you can see some pictures of it. I just didn't get the links and I didn't use any of their pictures, so I wouldn't have to violate or be on the borderline of violating copyright laws. But I'm not charging for this, so it's free. You can publish this, send it to your friends as whatever. If they're studying for their extra exam, give them a copy of this. It's free to distribute to anybody. As long as I've got this down here from Gordon West that produced these schematic diagrams of these 3 oscillator circuits, and now we're going to have to figure out which is which and why they're like they are. So what we're going to do is called circuit analysis. That's where you go in and you identify every part and identify its purpose in the circuit. The one thing common to all 3 circuits is, first, they're oscillators. Second, they use a JFET as the active component. It makes the amplifier. And third, they have inductors, capacitors, and resistors. The JFETs don't need many resistors. There's just 1 or 2 here and there. And one of them uses a crystal. Now let's start on the top left circuit and identify where's the feedback path. Well, in a JFET amplifier with grounded sources, this is like a common source amplifier. The source is hooked to ground, and this in this circuit, it's directly hooked to ground. And the gate is like the input of the amplifier, and the drain is the output of the amplifier. So if you've got input on the gate labeled G and the output on the drain labeled D, there's a path straight between the drain and the gate. So that would be our feedback path. Goes through C2 and through the crystal. Now this is the most simple representation of an oscillator, and identify the function of these components on here. C1 on the gate and C3 on the drain are bypass capacitors. That means that they're very low frequency, no, not C3, C4. C1 and C4 are bypass capacitors. They're very low impedance at the signal frequency. Now C2 and C3 that's on the drain circuit are there to load the crystal to the correct capacitance. Because for a crystal to be on the right capacitance.
Wayne,
Hello.
C2 and C3 are on the drain circuit?
They're connected to the drain.
I thought C4 is on the drain.
It's also on the drain, but C4 provides the output. The little circle on the end of C4 means the terminal that you connect the output to.
Okay, I guess I got confused then.
Well, I'm sorry, I said the wrong number to start with and confused you.
Well,
So,
there's also a problem in the diagram. There are a lot of diagrams that do not connect wires or lines that cross, but in this one there should be a dot. The convention of using a dot to show connection.
yes.
And that makes it unclear. But you've got L1, you've got C4, you've got C3, and you've got C2 all coming off the drain circuit.
Right.
The other problem with this diagram is
There's a
that
dot there.
the other problem with this diagram is that the power supply voltage, instead of being shown at the top, comes down to the bottom with L3. And it would be clearer if that line went up instead of down.
Okay, let me switch to another view of this.
Yeah, the orientation on the drawing is really bad.
What I'm
Well,
gonna
they tried
do-
to they tried to adjust it so, and you know, orientation is not always clear on schematics. Look at anybody's schematic on a
Okay.
computer module.
All right, we're going to start over.
Ground on the bottom, you bust on the top.
I love it. That's the way you wire it, actually.
That keeps everything clean.
Let me start over.
I didn't mean to derail this or anything, but I just got confused. I'm sorry.
No,
Okay.
that's okay. That's if it's not clear, then we need to clarify.
Yes, the normal way that I draw schematics is if two lines cross straight over each other, they don't connect. Unfortunately, this Gordon West does not adhere to that convention.
Well, he's got dots there. They're just really, really small. You can see them at each one of the intersects.
You see two lines cross in schematics, one will loop over the other like that. Can you see what I'm sharing now?
Yeah, I got you. And I'm used to doing network drawings as well. I am a network engineer. And once I forget who said it, but I do see the dots, and they are very small. So once someone said there was a dot there, I did see the dot, but I didn't see it at first. So that's where I got confused.
Dots are very small.
Very small.
I will agree with that. Well, these are not my drawings.
No, I got you. I got you. Thanks.
I will enhance the dots.
Yeah, I got you, Wayne. Thanks.
All right, sorry, I didn't do that on the printed copy. That's why on your printed copy, take your pen and make the dots really big and thick like that. So, because normally when you draw schematics, you do it like this right here in the middle of the screen now. One line is straight and the other one loops over it so that you don't get confused.
Yeah, and the problem with that is that if you're doing a diagram of 32 data bits, all those squigglies that cross over get extremely confusing.
Oh, it is. Even reading some of the service manuals for HF transceivers, which I do a lot because mine tend to break, 4 or 5 lines with these squiggle humps over crossing wires gets to be really bad, really hard to follow. Okay, so back to our discussion of the circuit analysis of this first one. C1 and C4 are bypass caps. C2 and C3 I call RF capacitors because they have a certain impedance at the RF frequency. I'm assuming this is a RF. It doesn't have to be RF. I mean, there's 100 kilohertz crystals. I've got one in a real old receiver, my first Drake receiver, that's 100 kilohertz. But usually these are in the megahertz range, typically from 1 to 20 megahertz is the normal range for crystals. So these would be RF capacitors, C2 and C3. The C4 and C1 are going to be bypass capacitors. The JFET here is an amplifier. So we see that the feedback goes from the output through C2, through the crystal, back to the grid, like that. And you can draw that path on your page or make a note in your book. The L1 right here is the choke. It's a high impedance, and we'll study impedance when we get to components. But see what it does, it brings in the voltage to the drain. That's supposed to be an H for high impedance. It brings the voltage from the power supply into the drain to make the amplifier operate. And the resistor on the grid is like a grid leak resistor. Whoops, I missed a dot down here. It's like a grid leak resistor, And it'd probably be a good idea to take your pen and make those dots big so you can remember what's connected and what's not on these diagrams. Okay, now we're going to move to the right and talk about the circuit analysis of this oscillator. It's a little bit more complex, but let's start with something we know. For the drain, we have the power coming to the drain, and the C3 is going to be a bypass capacitor. So that's going to make this a common drain amplifier because the gate and the source are neither one are grounded. I mean, you can have a transistor operated with any of its 3 pins as ground. This would be a common drain amplifier. The first oscillator we looked at was a common source, and you can also have a common gate. Each of them have different properties that are useful in different types of circuits. The output right here is going to be another bypass capacitor. I guess I could label it BY for a bypass capacitor. Then on the gate, you've got a gate resistor again, which gives the transistor some bias voltage. And the feedback path, well, if the output comes off the source, that's going to be the output and the source of the feedback. So it's got the signal has to get around here and get back into the input, which is the gate. So that's the feedback path. Now, what components does it go through to get there? Well,
Doesn't it go through the choke on your feedback loop?
Yep, it goes through the choke. Let me redo that. That wasn't very clear. I'm sorry. We come around from the source as the output through the choke and through C1 back to the gate. Now C2 is in there, also connects across the choke to ground, and that's a good way to change the frequency because the resonant frequency will be given by the partial part of the choke that's tapped into the feedback circuit with C1 and C2. Now the grid has a little bit of capacitance. I mean, not the grid, the gate. I'm sorry, I'm thinking tubes again. The gate has a little bit of capacitance in series with another one, makes a smaller capacitor. So C2 is the primary capacitor that resonates with L1 to set the resonant frequency. Now this is good for making a variable frequency oscillator or a VFO. So one thing that we needed to do is identify the names of these oscillators. That's part of the study questions. This first one, C, comes off of 2 capacitors that are going to be act like a voltage divider, just like this choke is tapped. Well, this is a tap that comes off 2 different capacitors, C2 and C3. So this is going to be a capacitance tapped oscillator, and a capacitance tapped oscillator is a Colpitts oscillator. Is an easy way to remember that one. Now, what units are inductors measured in? Inductors are measured in henries, and probably for, well, that looks like a wire. So let me redo that. This is supposed to be microhenries for the choke. Inductors are measured in henries. We tap the choke to pick off the part we want to use. And the tapped inductor also brings in the operating voltage to the source. And see, the operating voltage is blocked by capacitor C1 from getting to the gate. So C1 blocks the DC, it passes the RF, so C1 has to be an RF capacitor. C2 you can call the tuning capacitor, and this makes a VFO. Everybody see that, how that works? The drain is grounded, so this is a common drain amplifier. You don't need to know that. It's just part of the circuit analysis. You do all this circuit analysis so you can see where the feedback path is. And here we have the feedback from the source to the gate, goes through the tapped inductor, which is measured in henries. So this becomes the Hartley oscillator. Oh, and I see I made a mistake. The first one. So go back to the first one and erase the coal pits. That's not right. That's called a Pierce oscillator, like it's labeled in your book. See, I was trying to see if anybody's watching. So I assume most everybody's watching and absorbing all this stuff and not looking for my mistakes. This is a Pierce oscillator. Let me get my eraser out. Whoops, it has a gray background. That's just the way the picture came out. Pierce oscillator can be remembered by having this feedback path, having its feedback path in parallel with the amplifier, just like up here in this first one we drew. See how the feedback path, let me draw the feedback path on this one, comes off the output through a bypass cap. It's in parallel with the amplifier. Pierce is like a parallel oscillator where the feedback path, we label the feedback path here. That's what I didn't do the first time. That's why I got off. I'm sorry. I misled you. So the feedback path is in parallel with the amplifier. The JFET is the amplifier. We'll label it amp. Feedback path in parallel makes a Pierce oscillator. The feedback path through a choke over here, which is measured in henries, is the Hartley oscillator. Okay, so everybody straight on that? I hope I got that straightened out for you. The Pierce oscillator is good for fixed frequencies because the crystal is not going to change much. There's a way you can change the C2, but when you do that, you're also changing the feedback path. Not recommended. If you want to change the frequency of the crystal, like to set it on the right frequency, you would put a very tiny capacitor across it, but that's beyond the scope. So remember that the Pierce has its feedback path in parallel with the amplifier, and it's good for fixed crystal oscillators. The Hartley that gets its feedback path through the tap choke measured in henries is good for VFOs, where C2 would be the tuning capacitor. And we're still looking on page 141. This third oscillator circuit, start working on it. Well, you know what the amplifier is. That's the JFET. Voltage supply comes into the drain, C7. has to be a bypass capacitor. So that makes this the grounded drain, common drain amplifier. Here's the output coming off the source. So that's going to be the start of our feedback. So C6 down here has to be a bypass capacitor. And again, here you cross the wires at right angles. And this is intended to be a junction, not the wires not touching, which is bad schematic drawing practice. But this must be an old diagram before that became a pretty good convention. So I always draw schematics. If the wires are going to connect, they connect at right angles. If they cross like this, they're not connected, although I'll usually draw my schematics with the loop over, so it reminds me that they're not connected and it's not ambiguous in case the dot is really tiny and about the same size as the line and comes out. Let's see, whoops, here's our ground bus, our common connection down here at the bottom. It's not ground. So we've got the connections on the diagram like that, right? Did I get them all? Okay, so if we've got a bypass cap on the drain, a bypass cap from the output coming off the source is going to be the start of the feedback path. The gate has to be the input to the amplifier. So where's the feedback path in this guy? It's mostly through C4 and C5. Here's where you get the tapped capacitor, much like the Hartley had a tapped inductor. This is a tapped capacitor, so we'll call this the Colpitts oscillator. Sorry for the previous confusion. I needed to watch the circuit analysis I was doing and realize what was going on. So the source, and I kind of drew the feedback path a little too wide, so we can erase part of that. And the feedback path comes around from the source to the gate and goes through this tapped capacitor C4 and C5. So these are RF capacitors. They're not bypass capacitors. They have some impedance at the frequency you're oscillating. Now, what's going on here with the other circuit? In parallel with this tapped capacitor circuit that makes it a Colpitt oscillator, it's got an S, Colpitts, named after a guy that invented it way back. I think I saw it was 1908 somewhere. Is that in the book? I don't remember if that's in the book. That's Google Colpitts oscillator and you'll get all the history behind it. So C3 could be a bypass capacitor, and you can vary the frequency by changing the reactance across the tapped capacitors C4 and C5, just like up here in the Hartley oscillator, which, by the way, he left out an important bypass capacitor. The power supply is always got a bypass capacitor across it. So he left that one out. So we'll add it up here.
Yeah, the other piece of that, Wayne, is the VDD is the same connection.
Yes, VDD is just the power input.
Yeah, and so
Right.
it has two different places,
okay.
But it really is connected
VDD
together.
up here, right? I just wanted to have that comparison because the bottom end of L1 is RF ground, which is through a bypass capacitor, in the Hartley. And so at the coal pits, the bottom end of the tap capacitors is down here. Did he leave off another one? The RFC is the choke. I guess you could have a bypass capacitor here and call that ground. This diagram in the book is kind of incomplete.
There's a line missing because the way it's drawn.
Because you need a resistor here to give it some gate bias. Otherwise, the amplifier is not going to work. This can be big, like megohm range or 100K. But we're not here to design amplifiers. We're here to design oscillators. But an oscillator requires an amplifier to work and a feedback path. And the Colpitts oscillator, the feedback path is through the tap capacitors with this auxiliary frequency setting circuit over here. C1 is the tuning cap. And you can turn this into a VFO. Okay, too much time on that. So let's look at the questions. Well, we don't have the questions yet.
Can I ask you a question? Can you fix that so I can print it?
I will take these notes that we've drawn on, and at the end of our session right here, I can put a copy of it in the chat, and then you can take it and save it and print it.
That sounds great. Thank you.
All right, I can do that. Yes, that will be possible. Just somebody remind me when we're done, if I haven't done it before we end and break for lunch.
Or you could email it to me.
Well, the easiest way while we're on Zoom is to, all right, well, I mean, we can do that and email it to the class, but if you want it immediately during lunch, I'll put the copy of it on the chat window.
Appreciate it very much.
That'll work. We can do it that way. Let's see, let's go up here and talk about a different type of method to make oscillators. It's called a phase lock loop. Now, let's see, what have I done? To where I can't get it all on the window anymore. We'll have to do it like this. Okay. So the phase lock loop is a digital thing. It started out being analog, but quickly advances in digital circuits and the speed at which digital circuits worked made this into a digital operation. It can still be analog circuits, but the phase lock loop is a servo loop. What it means is it's got a loop, and this is a feedback loop. But the oscillation doesn't come from the feedback. The oscillation comes from this VCO sitting over here. It's a voltage controlled oscillator. Here's the oscillator in a phase lock loop. And this is supposed to be frequency out over here. It looks like I'm trying to spell a word, but it means frequency out. F I used as an abbreviation for frequency. Phase lock loop depends on a reference frequency. A good reference oscillator would be our Pierce oscillator over here that runs on a crystal. So if you've got a fixed oscillator, that can be a reference oscillator for the phase lock loop. There's this circuit right here called a phase detector. What this does, if you've got two signals coming in and they're about the same frequency, but slightly out of phase, then it's going to give you a voltage over here. It's going to give you, well, it's going to have high frequency components in it, which is why we need the low pass filter. And so here there's a delta in phase, which is what the phase detector provides for you. This is delta phase, and you out of the phase detector, you get a DC level with some noise, AC high frequency stuff on it. And so you have to go through a low pass filter to get just a low frequency signal or DC. And you can use this, oops, I forgot my dot right here. You can use the phase lock loop as an FM detector. You pick off what comes out of the low pass filter. Now, obviously, if you want to get the audio from the FM detector, it needs to be in the audio frequency range, which is around 3 kilohertz. So here you would set your low pass filter around 3 or 4 kilohertz, and that's the audio you're getting out. This is an amplifier right here. The triangle drawn like this is always an amplifier, and it goes to an oscillator that's making a frequency out. Now, if you're using this as a synthesizer, which is a synthesis part of this conversation, you put in here from the frequency output a divider. This is a digital divider, such as a divide by 10 digital divider circuit. You can make any T, this is supposed to be an A and an L. It's a digital circuit. And what's neat about a phase lock loop synthesizer is you can change this divider. And in fact, that's how the first FM transmitters were made. You had switches that would set different division ratios to take the output frequency and change the division ratio, feed it back to the phase detector. That would change the DC coming out of the phase detector and feed it back to the to the voltage controlled oscillator, and then the output frequency changes. That's how you would set different FM frequencies. So instead of having just crystals like the first FM radios would have, the phase lock loop lets you set here with different digital division numbers, and you can change these during your operation to get different frequency outputs. That's a phase lock loop. It's got a feedback loop. Here's an output, goes through the divider, goes back to the phase detector, gets filtered, and goes back to the oscillator. This oscillator can be some of these, either Hartley or Colpitts, and a VCO would work with a variable voltage coming in here to a component that would change the capacitance based on this low frequency or DC voltage coming in here. That's supposed to be a D, and this is a C for DC, very low frequency. And so the phase detector compares two frequencies, comes out with a DC level, it's low pass filtered to get the ripple off of it. And if you set that about 4 kilohertz, you can pick off the audio if you feed the incoming RF in here for the frequency reference, and then get the audio as an FM demodulator. Now let's talk over here about the DSP functions. Now you guys are fortunate because in 15 or 20 years, instead of just recognizing the functions of DSP circuits, you'll have to be recognizing bits of computer code that perform these functions, because every one of these functions can be done, I guess with one exception of a low-pass filter. That's still analog, although you can make low-pass filters in a DSP. It's called an average. But most DSP things now would bring out a pin for a low-pass filter and then take it back into the DSP processor. Phase accumulator. What a phase accumulator does is to make a sine wave output. The phase accumulator adds up the little bits of phase difference all along the sine wave as it goes up here. While the sine wave voltage is rising very fast, the phase difference between each of these little pieces is very big. Now up here where it's flatter at the top and not changing much, the phase differences are very small. When the sine wave is decreasing, the phase differences are negative. So the voltage, this is the voltage of the sine wave, and the phase accumulator just adds up the little bits of phase difference. Another method of doing a DSP synthesizer is you have a lookup table. Lookup table can be contained in memory, in digital memory, and you use an oscillator to step through the addresses for each of the digital words. And I built one like this before I even knew what digital signal processing was. And all it does is you take samples, you calculate samples, it's all mathematics, of the sine wave, the voltage of the sine wave. So each of these points on the sine wave has a voltage. You store those in digital memory. You use an oscillator, such as any of these oscillators over here, or other types of digital oscillators, and you run this to a D to A converter. Out comes your sine wave, represented by the mathematical value of the voltages at each step along the sine wave, and this is called the sampling frequency up here. At the frequency you sampled the sine wave at is the sampling frequency. Now the neat thing about this is the first 4 components in the DSP can be used, or is called a we'll get to the question. These first 4 are used as a direct synthesizer, a direct digital synthesizer. You can abbreviate it DDS, direct digital synthesizer. Okay, however, by doing this, there's a little bit of noise because you don't exactly represent each value of this sine wave. So you're going to need a low pass filter to filter out this real high frequency noise, because the D to A converter isn't going to interpolate between here. All it knows is the digital word that you sent to it. So this voltage comes out and then this voltage comes out. So for this amount of time, this is the voltage you get out. It's just straight across. Then the voltage jumps to this sample and the voltage is straight across, and it jumps to this sample, and here it's straight across. And then the voltages start down a little bit for each of these samples where the sine wave is increasing or decreasing. There's steps in there, and those steps are spurious signals. That's the spurious signals, or the steps from switching between the digital outputs. And so it takes a low pass filter to get rid of that. And that's why a direct digital synthesizer has to have a low pass filter. Otherwise it's got all this noise in it. Another thing that can happen is if you've got a real coarse sampling because your frequency that you digitized your data for this direct digital synthesizer is too coarse, you're going to have phase noise. Now, everybody remembers from last week when we talked about receivers. What's one of the problems of having excess phase noise on your local oscillator? Anybody remember the term? It's called reciprocal mixing. Well, here's where the phase noise on the local oscillator is made. If you've got a direct digital synthesizer and the low pass filter is not very good, you're going to have phase noise, and reciprocal mixing happens when you have this phase noise on your local oscillator and the input of the receiver gets a very strong input signal. And that input signal mixes with this phase noise, which is not at the frequency of your receiver is intended to be tuned to, and gives you on-channel signals that go through your IF. Now, this sampling frequency has a property called the Nyquist rate. Mr. Nyquist was a scientist at Bell Labs in the early days of telephony, and he had to know what was the minimum number of samples of an analog signal you can have to where you can recover the analog frequency after you've transmitted it by digital means. And the answer is at least 2 times the highest frequency component is what it takes to do that. The A to D converter sample rate sets the maximum bandwidth. So you can see if your sampling rate is not fast enough, the A to D converter is going to miss details in your incoming sine wave. Like if your incoming sine wave had lots of changes to it like this, and you go sample here, and you sample this voltage, and you sample this voltage, and then you sample this voltage, and this voltage, and this voltage, you're going to miss a lot of information in that higher frequency signal. So you've got to have at least 2 times the highest frequency component in your A to D converter, and that sample rate is what sets the maximum bandwidth that can get through the A to D converter. The A to D converter has limitations by the, well, no, that's a different part down there. Okay, let's talk about the A to D converter and how it can convert. If it has a range of 1 volt and you want to get a resolution of 1 millivolt, that's 1,000 steps that you need in your A to D converter. So the question will be, how many bits does it take for this A to D converter to represent these 1,000 steps? Well, if you're a computer guy, you know that 8 bits gets you 256 steps. That's how many digital values can be contained in 8 bits. So 9 is 512, and 10 is 1,024. Now the book has the example of how you figure this mathematically using the anti-logarithm, but you don't really need to have to do that. I mean, when we first started doing A to D converters, not everybody was computer savvy, so we didn't immediately recognize that 8 bits was 256 values. So it's easy to see how you get from 8 to 10 bits, you get 1,024 steps. So 10 bits will do these 1,000 steps, a 1 volt signal into the ADC with a 1 millivolt resolution. The FFT is called a fast Fourier transform, converts signals from this analog domain. Seeing a sine wave on an oscilloscope is a time domain, and you can convert time domain signals to frequency domain signals using a fast Fourier transform, which is abbreviated FFT. FFT gets you to the frequency domain. And it's very easy in DSPs to do operations in the frequency domain. That's what DSP code is all about. That's its strength. One thing about bandwidth is you use decimation to reduce the sample rate. So the sample rate can be reduced by 2 or 4 or any number by the use of decimation, and it reduces the bandwidth. So it goes back to Nyquist. When you use fewer samples on a signal, you reduce the bandwidth of that signal. And it all goes back to Nyquist. Nyquist was one of the early pioneers of signal processing, and it's still used all the time in digital signal processing because you have to keep in mind the number of samples. The A to D sample rate sets the maximum bandwidth, and use decimation as one of the operations in a DSP. All these operations here can all be digital inside a DSP. And I don't know why he threw that into oscillators and synthesizers, but that's how the book's arranged. A software-defined radio. We talked about this in receivers. The software-defined receiver is limited by the voltage reference and the number of ADC sampling bits. And these two things set the MDS, minimum discernible signal. You remember that term from last week? Minimum discernible signal. Goes to our receiver chapter last week. If I can remember how to spell it, DISC, discernible signal. And in a software-defined radio, that is limited by the voltage reference and the depth of the ADC bits. ADC sampling bits is called the depth. I guess I could write that word on there. That's in your book. That's supposed to be an E. Like, how many bits does the A to D have? Okay, then there's DSP filters. Digital signal processing implement digital filters. One type digital filter is a fir filter. It's not like a fir tree or any type of tree. It's finite impulse response. So this is an abbreviation for finite impulse response. And it's a type of digital filter, and as differentiated from an infinite impulse response, and R is response. And what's important about the fir filters is that it delays all frequency components equally, because when you use a fast Fourier transform to convert analog signals to the time domain, what you get out are frequency components. And you really want to keep the delay of each frequency component equal. If you get those screwed up, it messes up your filter. We won't go into filter theory, but that's the bottom line of it. All frequency components are delayed equally in a fir filter. Dsp Filter Taps, which are used to implement the finite impulse response filters in the DSP, provide incremental signal delays. That's how a fir filter is built, by using filter taps. And the more filter taps you use, the better the shape factor. That means the sharper the filter response is. So more Dsp Filter Taps give a Dsp filter a sharper filter response, which we learned last week is a better shape factor. Its sharper filter response makes the filter better. So this is how Dsp filters are built. Now all this is coded in computer code. We're not going to do computer code, but that's how you build Dsp filters, using a finite impulse response to delay all the components equally, using digital filter taps to provide the incremental signal delays. And you have to remember that more taps gives the Dsp filter a sharper response, which is a better shaped filter. Now the problem here is that we've run out of time before our 12 o'clock lunch cutoff so that we can start back at 1. So John, what do you think about me going through the questions? I'll post the copy of this drawing on the chat window so people can have it to look at if they didn't take the notes down as we went through it, or they can print it out later. Can we do that at 1 o'clock and start with the questions for this section?
Yeah, there's no problem with that, Wayne. We'll just
Okay.
we'll do what we need to do. I appreciate the explanation that you've given for some of these really complicated things.
Some of these concepts, especially when you get to DSPs, I mean, all of this DSP work here is like 2 college courses in DSP. And we certainly don't have time, and we blew through an hour just going through oscillators and DSPs. And so I didn't do very good on the time management. I'm sorry about that. But let me save this off, and I'll post the copy of this as a PDF in the chat window so you can have this. And it'll be a different file name from before. It'll say oscillators and synthesizers -markup.pdf. As soon as I get this printed, I'll put it in the chat window. So at 1 o'clock, we'll take up and look at the questions in the book, starting on page, was it 141? And this is going to be printed, and I'll put it in the chat window.
Yeah, those questions shouldn't take long because you've explained all of them.
No, I explained all the questions. We'll just have to relate the terms in the question to the terms in the correct answer.
That's right.
And then we'll be set with this section. It's a fairly quick section, but can be confusing if you're not a DSP educated person.
Guru, yes.
I'm not a guru. I know about them. That's all.